So try to understand that. I don't know whether try to understand that basically, right? I am literally sacrificing my Sundays, family time with my, with my family, right? To conduct this class, right? So I think maybe like my objective is to just find a common time for everyone, right? Some people are like, they can't make it at this timing, right? Or something like that, and ask me to change. But you see, the thing is, if I were to shift it to somewhere else, that somewhere else everyone must be able to make it, right? Because it needs to be available to everyone. I tried even switching it to, like, let's say for example, maybe morning time or maybe early afternoon time. But some of you are like, oh no, I got time practice at school, right? Can you not hold it so early on a weekday, right? So if I cannot find any common time or any common thing with everyone, right, then you know what? I'm just gonna stick to Sunday, right? But I will, for this week onwards, right, try to see whether or not y'all can make it for other timings, right? It depends on what you want to sacrifice, right? I'm sacrificing my family time on Sundays to do this class, right? So if I were to shift it to, let's say, a weekday, and then you tell me like, oh, you got time practice and all that, I don't know how important is the time practice. I don't know how effective is time practice for you, right? If you have to switch it around, please go ahead and switch it, right? If not, I'll just take it to Sunday. Right? If everyone can't agree on a certain day, I'll just keep it onto Sunday, because that's what I can offer for now, right? And again, I mean, I'll be glad to switch it out. No problem for me. I'll be like, if I switch you guys out, I'll be done now. I'll go out. I'll just go and find my family. I'll go and join them for lunch, man. Right? Yeah. But yeah. I don't know which day does it look like. To me, it's either Monday or Tuesday. To me, it's either Monday or Tuesday. So if I were to create a poll Monday, Tuesday afternoon, right, and I'll switch this Sunday class to that Monday or Tuesday afternoon, right? Yeah, I'll be more than happy too, man. Cause yeah, and I don't want to put it on Wednesday, because Wednesday will be like Wednesday, Thursday. It makes no sense, right? So it's either Monday, Thursday, or Tuesday, Thursday. So at least that you have. I mean, yeah, I mean, I can shift these guys around, right? These guys are the IB guys, right? And I mean, they don't have things like time practices and all that, right? Basically, they're left on their own, right? I can shift them around. I can shift them up. I can shift them down, you know. But I think I prefer to put it around here like this, right? So if I were to put the J2 class, I switch the Sunday to this one here like this, it will be 4 o'clock. Or I swap them around. I put them at 4 o'clock. I put you at 2:15. So I should do a poll, maybe, right? I mean, I would love to. I mean, I would love to explore this idea of like switching over. I mean, I would love to go. I spent the one whole year, right? All my Sundays, right? Like teaching until 3 o'clock like this, right? I basically missed all my kids like activities in on Sundays, right? I would love to. I mean, if you know some other tutors, like they keep Sundays off. I'm like, what? How do you do that? I don't know, man. And how many Sundays do we have left anyway? How many more is there? 1, 2, 3, 4. Yeah, that's it. Like you also can argue like, what's another 4 more weekends without my kids, right? I guess you can argue that as well, right? It's just that's really harsh then, right? That's cold. What are you talking about? Yeah, but at least I get the 4, right? When you reach my age, right? When you reach my age and when you realize that mortality is a thing, right? And your kids are young, right? You probably will want to try to get as many days as possible. Like, go and ask your parents whether they want, right? These 4 weekends from you again. And they would love to have it back, right? I think they want to deal with teenagers, ah. Okay, so if possible, I would love to be able to shift it as well. I mean, I can also keep it as a spare consult day, right? It's like, as long as I don't focus it on Sunday, I can keep it like I do like a Tuesday, Thursday, and then come Sunday, I can do like some questions and all that, but it's just not a dedicated timing. Anyway, we'll discuss that next week, because this coming week ain't no way. This coming week I'm dead. This coming week is just, oh man, yeah. This coming week is bad for me, man. Yeah. Other things. All right, practical. You asked me about practical. When's the practical again? I forget. 22nd, 22nd. So there is a, yeah, I should do one here, right? Actually. So this coming week, one. Oh yeah, that's right. Oh yeah, that was the reason. That was the other problem. Yeah, that was the other problem. I can't, right? So I can't shift this one. Then push back another one, oh, and push back another one. Then we like it'll be this and this, and then yeah. So with three, yeah. So yeah, there you go. So in the end, I don't think I can move it around anyway, lah. So yeah. Anyway, okay. Yeah. Let me just do a quick check. So this coming Thursday, practical. Next Sunday, practical. 16th practical, 19th. Well, that's way too many practicals. So I'm not going to do practical now. What you want to do? You want to do practicals for the next 5 lessons? Huh? Yeah. So we start next Thursday, lor. Yeah, we start next Thursday. This week I don't think it's a good time to start anyway. Yeah. Okay. Back to what we were doing, and have you all thought of what you want me to revise? Quantum. Quantum is big. Which quantum you want? Oh, X-rays. Okay. Can you type in the group chat? Yeah. Request for revision. X-rays. The two of you? Pez? Who else? Rachel? Any particular thing that you want me to revise? Nothing really big pops out your head. Even after doing all the papers, you don't feel that there's any topic that you still have unsure of. Just say X-rays can already. What? What, Pez? What? Anything in particular that you might be thinking of? E-fields. E-fields. Have I done E-fields in a while? Have I done E-fields recently? I did E-fields recently. So if anything, I will have to send you my recordings. What? Before prelims. Oh, that was quite recent then. Yeah. Rachel Lee Wen, if there is there any topics that you feel like you want me to revise, please let me know. Okay, no sound. Okay. Yeah, just text it into the wherever. What? Where do you text it in? WhatsApp, is it? WhatsApp. Okay, can. All right. Unfinished business. Do I have any unfinished business with you guys? Any unfinished questions I haven't gone through yet? Past Rachel Lee Wen. I mean, I have some. Where? Oh. In the Telegram. Okay. We have a weird question here like this. All right. This is by Afni, right? Oh, okay. Was it our consult? Was it your consult, your prelim consult? It was online. So basically, what we're supposed to do here? You're supposed to mark out the atmospheric pressure, right? I mean, just remind ourselves. Okay, so we're supposed to mark out the. Let me sorry. I just need to make this a bit. Okay, what are we supposed to do again? Mark out the atmospheric pressure. They want us to draw change in pressure due to the wave passing through X. I have no idea. She said there's no front part. I don't get it. Right? I think there's a front part, right? No front part. Okay, fine. There's no front part. Okay. It has a frequency of 250 hertz. So what's the period? Zero point. So 4 milliseconds. Right? So the period is 4 milliseconds. So I expect to see one wave, right? Of pressure. So but they say pressure, right? Change in air pressure. So there are two answers to this. I remember now. There are two answers to this, right? Number one, right? You can say this is the change in pressure, right? Change in pressure. So you could either have positive change or negative change. So you could get something that looks like this, right? Yeah, I think that's quite okay already, right? So 1 and then 2. Okay? So you can have one wave like this, and then a second wave like that. Okay? 1 and then 2, like this. But this will be change in pressure. Change in pressure with respect to what? Change in pressure with respect to? Change from what? Change from atmospheric pressure. Right? So these regions here, right, will indicate that it's higher than atmospheric pressure, and then these regions here will be lower than atmospheric pressure. So according to a sound wave, what's this region called? What's that region called? The one with the increase in pressure, what's that region called? It's a compression, and the one that's lower, rarefaction. Oh, hello. Hello. Hi. Why you laugh? Depression. Okay, that's not what the sound wave has. That's what you have. Ignore her, huh? Oh no, yeah, I know, right? Okay, it's okay, right, right. Self-awareness is the first step of recovery. Right, so this is high pressure, and this one is lower, higher than atmospheric pressure, lower than atmospheric pressure. You cannot call this pressure. Like this graph cannot be pressure itself. Why? Because you can't have negative pressure. You can't have zero pressure. You can't have negative pressure. Zero is a vacuum. So if you label this as pressure, this is okay. I think the alternative answer was the actual pressure itself, which then you have to indicate that this is, maybe you just chuck this as atmospheric pressure, ATM, okay, atmospheric pressure, and then you draw a graph that kind of looks like, oh, the grid lines are curved, right? So you draw something like here, and then here, like this, then ooh, like that. Then this is how the pressure curve might look like for a sound wave. Okay, right? So your equilibrium pressure is here. Then you got your compressions and your rarefaction. So this is an alternative. I think both answers were accepted. I think I see the mark schemes. They all give 2 answers, right? So depending on what you want, okay, what you have, right? But this should be the correct answer. And of course, you do the other wave as well. Okay, let's settle a couple more questions. Okay, unpolarized beam passes through a polarizer, copy image, and then she's asking, state and explain the intensity of the transmitted beam in terms of I naught after passing through the polarizer. And let me copy this onto my PowerPoint. Okay. Oh, this is an interesting question because I haven't seen this in a while. I mean, we all know how to calculate this, but you have to explain it, man. How are you gonna explain this? You're supposed to state and explain. State and explain. Yes. What's... Huh? Wrong. It's unpolarized. Oh. Yeah, lah, it's half. Okay? Blah, 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 it's half. Okay, so the I is equals... So if you polarize, unpolarize like the first time, right, it's basically half of the initial intensity, right? Okay? Like, that's output. So the question is, how do you explain this? How do you explain this? So you can say that unpolarized light has what? Unpolarized light has... Yeah, oscillations in all planes, right? Oscillations in all planes, oscillations, right, in all planes. Okay, oscillations in all planes. And then what? So by polarizing, you are restricting, right? So basically you're pass through a polarizer. So what does the polarizer do? It restricts oscillations to one plane, right? Oscillations, right, to one plane, okay? And then what? Right? So oscillations in all planes, right, has two, right, main vectors or main components, right? Has two main components, horizontal, right, and vertical, for example, right? Or basically you have two main components perpendicular to each other. You can say perpendicular to each other, and polarization will only allow one of the main components to pass through, right? So only one of the main components can pass through, right? And therefore it's 50%. Okay? So that's the answer to that. Right? Two main components perpendicular to each other, for example, horizontal, vertical, and polarization only allows one of the main components to pass through. Right. So it's not a filter, it's a restriction. Right. Please make sure that you understand this, right? And don't write filter as well. Right. We're not filtering all of the directions and only allowing one direction to come out. We are basically restricting it into one component. Right. So anything that's horizontal, for example, if your polarizer is vertical, anything that's horizontal will not be allowed to pass through. But it's not a filter, okay? All right. Okay, let's go on. Yeah, I'm gonna screenshot this. I'm gonna screenshot this to the to her answer. I need to reply to her answer. I mean she's asking whether or not her answer is correct. I actually can't really read her handwriting, but okay. Okay, she's gonna watch this recording. She's gonna kill me. Sorry. Pez is asking an AC question. Is that right, Pez? Yeah, yeah, okay. This is his AC question. I'm just gonna copy and paste it over. Right, let me just sort out all this first. Then we get back to the paper proper. Hang on. So power of this kettle is 21 to 25. Wow. Okay, 220 to 240. Frequency is 50 to 60. Goodness. Wow. Is this a new question? This is a new age question, is it? Where did it come from? Where does this one come from? TMJC 2024, is it? Teaching them life skills, huh? Yes, you would notice that this device can work in Malaysia and Singapore. So Malaysia uses 220 volts, Singapore uses 240 volts. So this is one of these cross-border appliances, right? Okay. No, I mean it is right. It is what it is because some countries uses 220, some countries uses 240. So which of the following is a probable expression that expresses the current that's flowing through the kettle when it's operational? Damn. Oh, weird ass question is this? Oh, actually, it's a good question. Have you ever seen them using this for AC before? No, right? I think rarely, right? Which is good. Yeah, it's good. Yeah. That's a bit weird. That means the guy who set the paper probably was an electrical engineer. Okay. Yeah, but this will never appear on the label, lah. You put this on the label, nobody understand what you're doing. What do you think this is? That will be the peak current. Good. Peak current. So you gotta find the peak current. Oh damn. Oh, you know what's the worst thing? What's this? And what's this? This is average power. Yeah. 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 So this is RMS voltage. Yeah. No, it is. It is. Like, ain't no doubt about it. That means you got to find the like no the legit peaks. That means you got to find the bottomest of the peak and the toppest of the peaks. for the peak current. No, you understand? No, it's not changing all the time. It depends on where you plug it in. Like I say again, if you plug it in Malaysia at 220, then the power is 2100, and then you will have a certain RMSV. The question is asking you to select one of these things that falls within this range. But you have to go and find the peak. You have to find the ultimate like peak values, like, you know, yeah. Okay, if it's 220, if your V is 220, right? Your V is 220. What's the peak voltage for 220? Peak voltage for 311. How did she get that? Yeesh. What's that? Times √2. Okay, that's not that hard, right? It's an interesting question though. Right, so this is no. Alright, 220 times √2. Alright, and what do you get again one more time? 311 volts. How about the 240? What's the peak for this one? 340 volts. Okay, good. Alright, next thing you need to do is you need to find a peak power. What's the peak power for this? There you go. What's the answer for that? Right, 4200 watts. And what's this one? 5,000 watts. 5,000 watts. And your job is to now find what's the range of the peak currents. So based on the peak on the peak power and the peak current, peak voltage, what is the peak current then? What's the two extremes of the peak currents? Finding peak current, use peak voltage, peak power.
But you have two peak voltage. So
Yeah lah, range. I want a range. I want a range, man. Come on, get with the program. So this one is what? This one is 13.5 amperes, and this one is, what's that? 14.7. Then you get the answer already. You know there's not A or B, or not A or C anymore, right? The peak, right? That means when you operate this device either in the low voltage or the high voltage, right? When it's low voltage, the peak current is 13.5. When it's high voltage, the peak current is 14.7. That means 10.4 is not a possible value to you to get. That one is a different issue. That one's a different issue. Your SHM, right? You remember SHM? Why? No, so anything in between is okay. Because I can plug in any voltage from 220 to 240. I can plug in maybe 230 and all that. So anything is in between. Anything between these two values can be the peak currents on this list here. Because this equation is your SHM equation, right? The peak value is this one. Yeah, that's the peak value, right? So 14.1 is possible. So it's either B or D now, right? Either B or D now. What?
What if the 2,500 watts and then I have a 220 volts? So that's 5,000.
When you plug your device with 220 volts, it will not run at 2,500 watts. Because
I'm so confused.
No, if you give something low voltage, you want it to run at high power. There's nothing to be confused about. Do you think you can plug something at low voltage and expect it to run at high power?
But got that weird graph though. That's like the is that there's some weird graph. It's fine.
One more time. Because I don't want to spend time fighting you against it. You plug in low voltage, you get low power. You plug in low voltage, 220 volts, you get low power. You plug in high voltage, you get high power. It's 2,100, 2,500, okay? Right? There's no such thing as you plugging in 220 volts here to get the high power 2,500. That's not how labels work. It's a bit worrying because it's a bit like life lessons, you know what I mean? It's like general life, like, you know, like your ability to survive in the real world, you know what I mean? That's a bit worrying, okay? Right? Yeah. Okay. What else do we need? Oh, 2 pi f. Right? Because the frequency could either go from 50 to 60. Right? That's a weird question. This guy's confirm the teacher is an electrical engineer. Nobody would think of doing this kind of question. Yeah, but it's interesting lah. It's quite a legit question lah. I mean, I'm fine with it. Wait. Do you get your 2 pi f? What's your answer? What's the answer? 50 hertz. Does it have to be 50 hertz? What?
60
So 60 hertz is what? 377. The 2 pi f is 377, is it? And this one is what? 314. So it cannot be B already because it's 300 only. So D is your answer. Sorry, Paz, what's the question? Yeah, bro. Okay, dude. All appliances run on AC, otherwise specified. Yeah. Like the only devices that run on DC in your house is the charging port of your phone. That's the only DC thing. Everything else running on AC. The power supply is AC. This is a prerequisite that you need to know from Sec 3, Sec 4. You got that? Okay. No, I think the bigger question is this: how do you know that this was average? Right? You see how I immediately declare that if you have a label here, the voltage here, they give you 220, 240. Those are not peak values. Those are RMS values. Right? Why? Why, guys? Why? Why is it that the label, right? Why is it that the label is not giving us the peak values? How come the label? How do we know the label gives us this is RMS values?
Because in your household, they also use the RMS.
But why? Why do they use RMS values for households? Correct. It's a general understanding by the mass population, right? Not everyone's a physics student, right? So the idea here is that they give you like the general idea, right? The average value, right? The average value of voltage, okay? But in reality, what happens to the voltage of your supply? Your supply actually fluctuates between positive 340 and negative 340. You get what I'm saying? Like your AC voltage supply will go like this, right? Okay, this will be positive 340 and this will be negative 340. Yeah, right. But you cannot go around telling people that, hey, right, your voltage supply is 340 volts peak. Nobody will understand what that means, right? And the worst part about this, if you tell me that that's a peak value, I'm gonna just divide by 2 for the average. That's wrong, right? That's wrong, right? So they would all these values are all average and RMS values. Good question though. Like I'm quite like refreshed by this kind of like questions here, because there we go. Okay, right. What's this about? Who sent this? You. Okay, yes. Yeah. What's going on here? What's happening? What's happening to this thing here? Okay. Right. As the metal sheet moves backwards, it tells you that the detected voltage is rising and going down, up and down like this, right? Okay. You can think of it as standing waves, but if you think of it as standing waves, it might be a bit problematic. Because usually for standing waves, we don't go and move the sheet backwards. It is possible to have a standing wave, right? The understanding is because the wave travels there and it reflects back, and then you can create a node, anti-node, right? So as you move your sheet backwards like this, right, it like you don't change the area stays the same. So the area will detect maximus and minimus, maximus and minimus. This is like detecting an anti-node and node and anti-node like this. Say what? Absolutely not. Yeah, don't see the graph like this and then think it's damping. Damping something must be oscillating, right? Where's the oscillation? There's no oscillation, there's only waves. Okay, so this is constructive destructive interference, right? So one of the other ways is this, right? The area receives a direct wave from the transmitter, and then it receives a reflected wave from the metal sheet, right? And then depending on the differences in the distance, right, you will get constructive and destructive interferences. Correct? Okay, good. So do you understand? Okay, I'm not too sure, but do you understand that if let's say right now it's a peak, okay, right now it's a peak, that means it's a constructive interference. Okay, constructive interference. When's the next time? How far would you have moved back by in order to get another peak again? There's a reason why the peak is decreasing, but that's nothing to do with this question. The question just talks about like if how far would you move back by in order to get the next peak again? Like what's the distance that you move it back by? What's that? Half lambda. Half lambda. Because The wave will have to travel this and then reflect back. So it has to travel this and then reflect back and then go back here like this. So this distance here is half lambda, but because it travels there and reflects back, it becomes 1 full lambda. If you say go back by lambda, it has gone to here. So it's only half lambda for the next constructive interference. Correct? Right? So that means that this distance here to this distance here is half a wavelength. Right? Because of the reflection. The reflection means that it traveled 2 times. Right? So therefore this one is, yeah. So that's a half wavelength. So the wavelength will be C, 120 mm. Okay, let's look at the next one. Oh, no more. That's it. Okay, good. We cleared it all. Oh, you just sent another one? I'm glad I don't see. Oh, sorry. I just saw it. Okay, one more for the road. Hey, but I thought I went through this. Yeah, I did. When Which paper? What's that? 2014 paper 1? Yeah, I did this before. I did this one before. But your working is correct, yeah? That's... Oh, you were copying. But what's your question after you were copying? Okay, so you shouldn't ask a question because the test charge must always be positive. Test charges, the moment you say test charge, right? In my head, right, I'm thinking of this. The letter test, the word test, right, is spelled with 2 T's. Test charge is positive. Okay? So there shouldn't be a question of what charge is a test charge. No way. Okay? The E field direction is always based on a small positive test charge. So if I say that, oh, this E field here is pointing this way at point P, this one is because of this guy. And this guy, this is not the test charge. This is like the real charge. The test charge is something that you put here and you ask yourself, if I put a test charge here, where does he experience a force? He'll experience a force this way, right? Due to this guy, and therefore this E field is due to this guy pointing towards the right. Then you drew another one here, you drew it there, right? Okay? So this E plus, this one here, if let's say I call this A, I call this B, I call this C, I call this D, right? This E plus, this is EA, right? The other one, this is EB, right? And this one here is negative, right? So the E field will point towards the negative, right? This is ED, and this one is EC. Yeah, test charge is always positive. There's no such thing as a negative test charge, okay? Right? But that happens from time to time. Some people, forget. Okay. Am I doing 2013? What are you thinking of? What the heck are you doing? Say some more IVSCO. Yeah, Visco. She said I'm a Visco. 13 Okay. Alright, alright. Wait, hang on. Have we finished paper 2?
No, we only did one question.
No. Wait, have we even started on MCQ? MCQ done already. Oh, the cable car, I was stuck here. Right, I was stuck here very long because all the forces. I had to go and fix all your forces, all these forces problems. You know what? I have this very freaking annoying constant annoying question that pops up every freaking year, and every freaking year I have to go and settle this question with them. Might as well just settle it with you guys. Let's see whether you can get this. Like this question here, right? So hang on, let me just clear this up first. No. You can't do this. You can't do this. This one's no. You cannot do. Wait, let me just. Okay. I think. Okay. Now, try this question. Try this question and go toilet. Yeah, I've been standing here for the last 5 hours. Just going puke. Yeah. Why you need to guess? Don't need to guess on it. Yeah. See, this is a classic case of see whether your forces are good, right? So, yeah, this is forces and dynamics. Remember last year I was teaching you guys. I was like jumping between forces and dynamics. Yeah, because I need to introduce you to forces first, then go through dynamics, then afterwards I go back to forces and moments again. Because otherwise you all don't know what's going on, right? For forces. Okay, come. I don't know, man. I'm just gonna look at this guy first. Okay, I'm gonna look at this guy. It slides over the trolley. Oh, actually, I mean, okay lah. I mean, according to that block up there, right? The friction acting on this guy is what? 3 newtons, right? 3 newtons, right? So the idea here is you have to look at the bottom object. Okay, the bottom object. Check if there's friction on the floor. Is there friction on the floor? Did they mention anything about friction on the floor? They never say anything. So what do? We assume that the friction on the floor is 0. Right? So there's no friction on the floor. But there is friction by the top of the block, like by the bottom of the block on the top of the trolley. So there's friction here, like this. Right? There's friction here like this, which is 3 newtons. Okay? So if you isolate your trolley and you draw the force of 3 newtons, then then that's the only force acting on the trolley. And therefore, the acceleration of the trolley is 3 divided by 4 kg, right? 4 kg. Yeah. So 0.75 meters per second squared. Huh? No, you don't want to know because it's none of your business. Yeah, this is an IB question, so kind of like, they use coefficient. Yeah, see? Yeah, right. So yeah, their kind of questions will be like, yeah, something to do with coefficient of dynamic friction and all. Okay, we good? Okay, then if you understand it, then it's not so bad lah, right? So if you're wondering, does it mean that friction is pulling the trolley forwards, right, causing it to accelerate forwards? Then the answer is yes, right? So get rid of the idea in your head that friction opposes motion. Friction can cause motion as well, right? Friction can cause motion. Okay, so we're done with that. I'm gonna switch over to the TYS again, right? Okay, and then we have what's this? Do I need to do this? So acceleration. So it accelerates for 2 seconds, and then constant speed for 120 seconds, and then decelerates the rest in 3 seconds. So total is 125 seconds, right? Okay, then the question asks you, they only want for the first 2 seconds. Yeah. So how does the acceleration look like for the first 2 seconds? How does the acceleration look like for the first 2 seconds? You see, Huh? What's going on? What? Am I not doing this question? Okay, so qualitatively, the variation of during the acceleration portion. Oh, sorry. Okay. The height, right? They're talking about height, right? Okay. So the height is what? The height is during the acceleration. Oh yeah, you're right. Sorry. Yeah. So it goes upwards like this, right? There's no values to it. So it has to just keep on increasing. So it's increasing its vertical speed, right? The man is increasing vertical speed. How about the height during the 2 to 120? What? Careful, No, I don't. Should we start at 0? Yeah, we can't start at 0. So it's a straight line like this. Yeah, we can't start at 0. Okay, you have to start at like an actual value. So in a way, kind of like this graph here, you have to draw it something like that, right? And then don't make it too high. You have to make it at 0 though. Sorry, I can't erase my thing here. Yeah. Yeah, they're just asking you, the deceleration part there and all that. Then the height will be what for this one, last one, right? So it will just be something like that, right? It'll be until it reaches a constant value. Okay. Yeah. Okay. Yeah. This isn't this a question? This is that question, right? Yeah. This one here where the acceleration is. This is a decreasing acceleration, increasing deceleration, decreasing acceleration, increasing deceleration again. Right? I think I went through this a couple of times already. Yeah. Right. I went through this a couple of times. Does anybody need anything here? Otherwise, I can point you to the video of where I've done this before. I hope I remember where it is. Shit.
It's like also probably
Prelims. Okay. Can. Hey, you want me to go through this quickly? No need. Okay. Hey, which one do you want me to go through? Come on, tell me. I got a request of 7. What? Okay, I got a 3B part 2, 3B part 2. Okay, hang on. But you know what? I want to know what's your 3A part 1 answers. Say in terms of force acting on an object, one condition necessary for object to move in circular speed at constant speed. Circular path at constant speed. What's the one condition? In terms of forces, what's the one condition? Be very careful, don't just quote the force, the resultant force. Yeah, all right, so make sure you write down the resultant force must be perpendicular to the velocity. Don't say speed, perpendicular to the velocity, right? The resultant force, right? Resultant force on object must be perpendicular to velocity at all times. Yeah. Okay. Object moves in circular path, has constant speed. Explain why it has acceleration. Sounds like a Sec 3 question. So why does it have why does it have acceleration? How do you explain this? Change in direction. Okay. Yeah. Velocity. Uh huh. Uh huh. Yes, that's right. Okay. So there's an acceleration because there's a change in direction of the velocity. Right. Change in direction, not magnitude of the velocity. If you want to make sure you just write down change in direction, not magnitude of the velocity. Okay. Very good. Yeah. What's the next one? Oh, 7B. Yeah, I mean, this Paz also asking for 7B. So I'm doing this one first. 3B, part 2. This one here. Radius of the orbit of the satellite is reduced. State and explain the effect on the potential energy and the kinetic energy. Hmm? Hey. Wait. No. Hello. Yes, orbital energies, right? What should we be thinking of first? Graph. That's the first thing you should be thinking of. I said this many times already, right? Orbital energy. The moment you see energy in orbit, right? Graph. What's the top graph? Middle? Bottom? GPE. Okay. So if the radius is reduced, meaning that the satellite has gone from a high orbit to a low orbit, right? So what happens to the potential energy? But why does it decrease? Why does the potential energy decrease? I mean, I know she's asking for the second one, right? But what happens to the potential energy? Yeah, correct. But you have to explain why. You have to explain why. Basically, you can say that you can basically say that there's negative work done, right, when the satellite goes closer to the planet, or you can say that there's a loss in GPE, right, as it goes closer to the planet, right, it loses GPE, right, the GPE value becomes more negative if you want, if you can write that down. Okay, so that's the explanation part, right? 1 mark only, don't need to over explain. You have to basically state and then give a short explanation. But what happens to the KE? Right, the KE increases, right? The KE increases, right? Pretty much you can say that that's due to what? You can say it's due to a smaller orbit, right? It's a smaller orbit, so the speed of the satellite increases. Or you can say that the KE of the satellite increases because of the loss of GPE, right? Some of the GPE is converted into KE, right? Some of the loss of the GPE is converted into KE. All right, let's double check and see what the answer key says. I gave you some of the schools one, right? Which one did I give you? Let's go with HCI. Let's see how weird they answer. Hang on, let's see. What's the question number? 3B part 2, 3B part 2. What did they say? Smaller radius has larger velocity and therefore larger kinetic energy. Okay, right? And then it says, yeah. You cannot use conservation energy. You can say some of the GPE. I never say that the GPE is converted to KE. Some of the GPE, right? You can say some GPE. Okay. But if you're not comfortable with this, then you can just go ahead and write, right? Smaller radius has larger velocity, therefore larger KE. Pass, okay? Why? Yeah. No, you're talking about the top one here. Yeah, okay. That's talking about GP and talking about KE now. GPE equals to GMM over R. Negative GMM over R. Okay, so this is 3B part 2. Done. What's the next one? What is meant by internal energy or ideal gas? What's your words? Internal energy. I want to see the word random inside though. I don't see the word random. You got to have the word random. Okay? So, yeah. So given by sum of microscopic Ke. Oh, ideal gas only. Sorry, I didn't see. Ideal gas. Okay, ideal gas. Yeah. You can quote that the PE is 0. Right? Yeah, you can quote the PE is 0. So this one is a contextual question, which means that it's not just a pure definition. You need to define it in terms of the context of what they want. They want ideal gas. So ideal gas is only the Ke. Right? Ideal gas is only the sum of microscopic Ke due to its random motion. Right? Make sure you have the word random. Microscopic might not be, because as long as you say kinetic energy of molecules. Yeah. Okay? Look at this. Sum and random must be in the answer. That's why I said key phrase, random. It's a thing. Last time in secondary 4, you don't have to write random, but now you have to write random for sure. Right? Because we need to recognize that these KEs are all statistical averages. Right? That's for 4A. Anything from 4? Anything else? I think nothing else. I think these are all calculations. Calculations, no problem, right? What is meant by photoelectric effect? Ho, 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 ho. It is what? Emission of electron from a metal surface when? So an EM wave of minimum frequency, of higher than the minimum frequency, sufficiently high, okay, also can. Incident on a metal plate. Okay, that's all fine. So your answer to this would be, let's see, where is it? Okay. Oh, why got cool one? It should not supposed to be cool. It should be clean. Okay. Liberated from cool metal surface EM on a minimum frequency, right, or sufficiently high frequency, like what you're all saying, right? It's incident on metal surface. Okay, right. So I wouldn't agree with this, right? I would definitely state that this is clean. Why cool though? Cool, clean metal surface, lah, right? Hot means that, okay. So remember what we mentioned about when you have a hot filament. Hot filament, right? Okay. In 2 instances, when there's a hot filament, what can it produce? It can produce electrons, or it can produce white light. So always remember that hot filament has 2 kinds of emissions. It could either emit electrons or emit white light. Okay? So maybe that's the reason why they use the word cool, right? Understand that, I prefer to use the word clean as well, right? On top of it, right? Clean, cool, clean metal surface. Right? But for you guys, your school used what? Sufficiently high frequency, right? The answer key here says minimum frequency, right? Sure, right? I think it doesn't matter. Yeah, okay, yeah, that's fine. Threshold frequency should be fine. Okay, so hot filament. Read the question carefully. Understand the context. It's either electrons or light. Choose what you will for the context of the question. Right? So yeah, hot filament produces white light. Okay? Hot filament also produces electrons. Read the question and see what the question is using. If the question is talking about spectra, then you use the white light. If the question is talking about like X-ray emission, then you use the electrons. You get that? Right? Don't insist that, oh, but I thought that you said that hot filament produces electrons and white light. Then electron fly to gas, what happens? Nothing happens. Right? The gas is in the tube. You cannot fly electrons through the tube. Okay, so that's for 6. Use theory of particular nature of electromagnetic radiation to explain why there's a threshold frequency for the electric. Send me answer. You didn't write it down? You never. Oh man. Who got write the answer down for this? Let me mark. You want to send me yours, Pez? Say what? Yeah, 6B. This one. I want to see anyone's written answer is fine. I'm just judging only. That's all. Marking, not judging. No, marking. I didn't say judging. Sorry. It's fine. It's okay. Let me just take a look, man. Come on, do it quick. Do it quick. Come on. Okay, let's do this, huh? Yeah, of course. There, bam. There you go. It's that's ugly, man. Walao, you haven't seen my handwriting yet. Okay, electromagnetic. Wait, what's this? Energy in discrete packets. Look, I see this thing as pockets. All right, photons. Okay, the energy of the photon is directly related to the frequency of the EM radiation equals HF. The metal surface has a minimum amount of energy required to remove an electron, known as workforce. They. You HR workforce, right? Work function. Since a photon can only excite, wrong. Photoelectric effect, we don't use the word excite. Excitation is you jumping up one level, right? Photoelectric effect is the entire electron is lost. It jumps out. It's completely coming out. So no way, right? So this one here will get you a loss of marks, right? You're like -1 because you're using the wrong concept. You get what I'm saying? Right. Since the electron can only since an electron can only absorb a photon at a time, you trying to use photon as a subject of your sentence here. So you should change it to electron. Yeah, since an electron can only absorb one photon at a time, the photon is required to have the what? Is this word appropriate? No, it's not about spelling. It's not the word shouldn't appropriate. Appropriate means what? You must have the correct form of energy, is it, or what? No. Yeah, sufficient or minimum, man. Right? To have the sufficient amount of energy to liberate the electron, right? Whoa. Suddenly you throw in which is the threshold frequency. Like your last part of the sentence there, suddenly throw in the threshold frequency. That's a bit weird. Okay. Wait. Okay, why there's a threshold frequency, right? Okay, so the sufficient amount of energy to liberate the electron, right? Which means the light must have a minimum frequency known as the threshold frequency. Are we good on this? Right? Yeah. Okay. Some of the things that I feel that's a bit missing here in your answer, right? Obviously, you are trying to describe this scenario here. Okay. Use the theory of particular nature of electromagnetic radiation to explain why there's a threshold frequency for photoelectric effect. Technically, there's only one thing that I feel that's missing, and that is the fact that why is there such a thing as a work function? Why does the electron require energy even in the first place? To do what? To overcome the electrostatic forces of attraction, right, from the metal surface. By saying that, right, that means that you are trying to, like, you're trying to show that you understand that the electrons are being bound to the metal surface, and therefore you're trying to liberate it. Okay, right? Rather than just you throwing the word work function here. Okay, but unfortunately for your answer, I mean, apart from the last part here, I mean, if you correct it, that's fine, right? If you use these two words here, I think -1 or -2, man. Okay, so be very careful. I think maybe a -1, probably a -1, right? Yeah, because there's only 3 marks left. Let's see what this says. So this is correct. So your answer here, there's this minimum energy to escape from metal surface, right? So proportional frequency, minimum frequency. So the answer here doesn't actually talk about the electrostatic force of attraction, right? I mean, there isn't one as well, right? So I think your answer is according to this answer key is sufficient. Okay. That's fine. Yeah, you cover all the points here. That's great, right? Except for the words. Be very careful with the words. So, like I say again, while you're doing all this, right? At some point, let me clear my this coming week first. You all saw my calendar. This coming week, the calendar is like I'm dead, right? The kind of calendar, right? It's like, brr, all right. I'm like, okay. So, by the week after, I should have a bit more time to mark your papers. After that, I'll mark your answers, right? So, yeah. Then you can start sending it to me and let me see. Okay. Okay. Seven. There's a request for 7B. Is it? Sorry, 7. Eh? But guys, I mentioned, right, semiconductors just skip already what? Really? Okay. Proposes that R is inversely proportional to theta, where theta is the temperature. That's so confusing. I thought it was the angle, right? Show without drawing a graph, this proposal is not correct. What do they mean by show without drawing a graph? What do they mean by that? I have no idea what that means. From what, 50 to 150, is it? 50 here to 150 here. Inversely proportional. Oh, okay, this is a legit question, as in like this is within your scope of doing work. That's fine, actually. This is you know that this is a thermistor. Do you guys know that this is a thermistor? Huh? Yeah, it's a thermistor. Oh, okay. See you, man. Okay, can bye. So this is the thermistor, right? I mean, especially for the this positive temperature part, right? The negative temperature part, right, is basically still a thermistor, but the coefficient changes. So you need to know that thermistors are made of semiconductor material. I was waiting for that. So thermistors, right? Thermistors are made of semiconducting materials, right? It's important to know. You know why? Cause what do semiconductors do? Semiconductors behave differently from normal conductors. So what's a semiconductor? What's a normal conductor? You got to remember the difference, right? What? Okay, a semiconductor is basically one of those elements on the staircase line. So silicon is a semiconductor. It edges between, if it's sitting on a fence between a metal and a non-metal. A metal is a conductor, a non-metal is a non-conductor. So a semiconductor is somewhere in between, right? What are the conductors that we have? Conductors, normal conductors. What are normal conductors? Example. Any metal, right? Copper, aluminum, iron, zinc, all those are normal conductors. Tungsten, nichrome, and all that. Yes, what's the question?
What's carbon? Is it a conductor or a non-conductor?
Carbon is just a conductor, that's it. It's just a normal conductor, but it's a non-metallic conductor. Yeah, you don't have to do anything special to carbon in order for it to conduct. But for silicon, you have to. Silicon, you have to do weird things to it. Yeah, okay. So the question is asking you, how do you check that this is an inversely proportional relationship? Like, is this a y proportional to 1 over x relationship, right? Yeah. So what must you check?
Multiple values.
You go and check 3 values. You go and pick out 3 values along this graph, and you go and check the r divided by the theta value. R by the theta value. 3. Don't ask for discount. 3. Huh? I don't care. I don't care. I don't care. My standard is you go for 3. Okay? Right? You go and find 3 values and you go and check whether or not the R divided by theta is constant. It's not going to be constant. Okay, you know what? You check 2, and if 2 is not constant, then that's it. Don't need to check 3 already. You get what I'm saying? You check 2, and if these 2 values are not constant, the K is not constant, the ratio is not constant, then forget it. Then just say it's not constant already. Good enough already, what, right? Yes, you're right. 2. Huh? Then you know my answer to that lah. Check 3. Huh? I don't know, less than 10%, less than 5%. Yeah, less than 10 or 5%. Okay? There you go. That's how. Does that answer the question, Lehman? Oh yeah. You just if you're a bit afraid about like how they will judge your answer, then you just write the coordinates here. You write the coordinates here like this, and then you just use the coordinates, right down here. Sorry. Yeah. Okay. Oof. See, this is just graph work, right? This is not like this thing is just graph work, isn't it? Yeah, it's just graph work, right? Yeah. This is graph work. This is
Can you take from this graph?
actually you can do this also. This one is just graph work also. Yeah. This is graph work as well. This one basically is supposed to lawn the graph. You're supposed to lawn this equation. Yeah. And then ask you why the graph supports this proposal. It's a linear graph with a positive gradient when you plot ln r uh against what ln r against t. Yeah.
Question 8 is like planning question.
Yeah, then don't do. Yeah, legit planning. Yeah. Wait Wait, hang on. Am I done with this? Okay, so this one is not doing. Okay. This one's only one variable, right? Correct? This is only one variable, right? This question here is only one variable, right? If you look at the question, only one variable, one independent variable. Don't do, because you're supposed to do 2 independent variables. Your plannings are all going to be 2 independent variables. You can't run away from it, right? Yeah, it's always going to be 2. So we're not going to do this one because it's like, yeah. Okay, so are we at paper 3 now? Paper 3, very good. All right. Anyone want to send me your answer for this? Why not? And then what's your answer for this one? Come. Gravitational potential at the point. What's she doing? What's she flipping? She's flipping her notes. Huh? Work done by external agent. Gravitational. No positive. Just test mass only, test mass. Oh. Work done per unit mass by an external agent in bringing a small test mass from infinity to the point without changing. Okay, good, right? The whole works, okay? So let's see this. Eesh. Whoa, what's that? Gross, 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 gross. Oh, I need to show the paper 2, paper 3 one. Work done per unit mass by external force in bringing a mass. Oh, bringing that mass from infinity to that point. But it's okay. You can go with for bringing a test mass, right? Work done per unit mass, bringing a test mass from infinity to the point. You realize that, yeah, some schools they have that without change in KE, some schools they don't have, right? Do your schools have without change in KE? You don't think so? Oh, they bracket it? Alright, which means what? That means you can write it down, and I would suggest that you write it down anyway. Okay? Alright, so just write it down. How about this? Do I need to go through any of this? No? Can do, no problem. What's the value for this one here? So what you have here is, this is what? This is 5,000, is it? 5,000. And then in order for the helium to be equals to the speed of the rock, the temperature needs to be 5,000 kelvins. Okay, suggest your reason. Okay, so this is one of the more controversial questions. Yeah, it is, because the answer is basically students are expected to know that Mars is not hot. Yeah, no. As in the answer key, right, says that it is unlikely that the temperature of Mars is so high. Yeah. You need a 5,000 Kelvin temperature for helium-4 gas, right, to have the RMS speed as the speed of the rock. Okay, right, as the speed of the rock that was yeah, correct. Okay, which, do you understand that this is escape speed? This is v escape in reverse. If you have a rock that's coming from very far outer space, and then it comes in and then it lands on Mars, and it lands on Mars with this speed, right? It lands on Mars with this speed. This is the escape speed of Mars in order to go back to infinity. Right? This is like the reverse scenario. Okay? What they did was they asked you, what is the temperature required? Sorry, this is not the temperature. It was the temperature 4,000 kelvins. I read it wrongly. 4,000 kelvins. 4010 kelvins in order for the gas to have the same RMS speed as the escape speed. What are they trying to do here? What are they trying to ask here? Like, why did they ask you to calculate this temperature for this escape speed? What are they trying to, like, you know? So they are asking whether helium-4 gas can escape Mars. Right? They're asking you whether helium-4 gas can escape Mars. Okay? So in order for helium-4 gas to have the same temperature, same speed as this V escape, the temperature of Mars must be this temperature, 4,000 kelvins, right? And the answer is Mars is not that hot. That's the problem. It's just slightly negative something. It's cold. No, it's not. It's the fourth rock from the sun. We're the third rock. Yeah. Yeah, Mercury, Venus, Earth, then Mars. That's right. So Mars is not that hot, which also kind of annoying, because it's like, huh, am I supposed to know that Mars is this, like, you know, it's colder than 4,000 kelvins? So this is one of those estimation questions. So the answer is yes, you kind of like have to know this, right? Yeah, unfortunately, okay. There you go. So what will happen to helium-4? Will you be able to find helium-4 on Mars? Huh? Mars is not that hot. So it's likely that it's likely that helium cannot escape. Right? So the answer is molecules at speeds higher, so her understanding of the universe is a bit worrisome. Okay. So all planets supposed to have elements, right? Whether or not we can keep the element on the surface of the planet depends on the temperature and depends on the gravitational field of the planet. So if it's not hot enough, then the helium that existed on Mars will stay on Mars. It doesn't escape. It's not talking about helium coming inside. Helium was already inside, like what she's saying. Helium was already inside Mars. Yeah. Okay, come. Do we need to do 2? Does anybody need questions from 2? Oi. Nothing, then I go and do her Bremsstrahlung already. So do I give you more time to finish this? Okay, Thursday, yeah? Right. And then by the end of today, I will assign you some practicals as well. We have to do some practicals already, right? To prepare you for your practical exam. Okay? Yeah, I know, right? And then we'll go on after that. So I think the rest of the questions are all very doable, bro. Don't look at it. Yeah, it looks very doable, man. Yeah, this is a weird. This feels a bit too easy. You have to make sure you get all the yeah. Sorry. The last one of this question is this thing is a pain, man. Yeah, the last part of this paper 3 is this is the painful one. Wait I think it was around this couple of years, 2013, 2014, when they started to introduce that stupid modulation thing into the syllabus for everyone, for all the schools, which is freaking annoying. Yeah, that one time came out, then all the schools all started teaching modulation. Yeah. Okay, so notes, X-rays, quantum.
Yes.
Yeah, bring out your notes. Quantum. Never bring then draw. Yes, there is. Isn't there? Is there any? It's gone. It's used up already, is it? Okay. Now let me just. What? Going home? No, like, go library. Go library and study. Look at her, she's all dressed up already for library. The big hoop earrings and all also. Quantum. Yeah, let me print out a copy for you. You know, I'm just gonna print out the whole thing for you. Oh, do you want a soft copy? Nobody can oh no. This is what I say, right? Like Roshni will make you stupider. No, I'm not gonna go through everything. Why? Okay, you know what? I tell you what, I'll send you no. I'll send you a revision I just did with my previous class. I was just revising this morning only. Yeah, I'll send it to you. But I did the exact same thing. Yeah, Telegram. Yeah, Telegram. You have Telegram, right? Yeah. Sorry. I'm not gonna do a full revision. I'm gonna ask you questions. Okay, what does photoelectric effect prove? What? Sorry. No, what does it prove? What is it meant to prove? That's yours. Oh, particulate. Huh? What? Wait. Shh. What do you say again? You said particulate light nature. Particle light nature. Particle nature of light lah. No me? Particle nature of light. Okay, particle nature of light. Okay. Yeah, that's a correct statement. Particle nature of light. Describe the experiment in a nutshell. Yeah. What do you shine? No. No, be more specific. Huh? Be more specific, not just light. Monochromatic light. So photoelectric effect, you shine specific colored light. On what? On what? On metal plates, huh? Yeah, clean cool metal surface, right? So on metal plates, huh? Okay. No, there was one A-level question. They ask you, aluminum oxidizes very easily, and I swear it's a physics question, right? They say aluminum surfaces oxidize easily. Describe what happens to the work function. Yeah, the work function will be higher because when it oxidizes on the top, it forms an aluminum oxide surface, right? Which makes the electrons, right? Requires more energy for it to escape. Yeah, I know, right? It's like what suddenly got some chemistry thing in it. Okay, photoelectric effect. You shine specific colored light on metal surface. What are you expecting to see? What are you expecting to see, or what are you expecting to observe? No, as in like you shine light on the metal surface. What do you expect to happen here? Yeah, so you expect the electrons to be emitted, right? Okay, into the collector plate. Okay, so the idea here is that you shine light on this, electron absorb the energy of the photon. What are the rules? According to quantum physics, what's the rule? What are the rules of this electron? What can the electron do? So the electron can only absorb one photon at a time, and the electron must absorb the photon that has the minimum amount of energy for the electron to escape the metal surface. Then it can be emitted. If let's say you give it a photon with more than the minimum amount of energy, what does the electron do? Or what does the electron have? No, not accelerate lah. It will have extra Ke. It will have extra Ke, right? So it will have extra Ke and then it will move over to this plate. Now don't use the word accelerate because accelerate means that it is going to get faster and faster, right? So it basically comes out and then it only has 1 Ke, right? What's the concept of Ke max? Why is there a concept of Ke max? What does maximum Ke represent? Ke max. You see, right? Not all the electrons will have the same Ke. Some of the electrons will have more Ke. Some electrons will have less Ke, right? So the one with the most Ke, right, is the Ke max electron. But why is there a concept of this? So all of them all have broken the electrostatic forces. So why is there one electron that is? So remember this phrase, huh? Right, remember this phrase, the most loosely bound. So the Ke max electron was the most loosely bound electron. Most loosely bound electron to the metal. Okay? Which means that this Ke max electron, right, is basically like he was just sitting right on the surface, about to go out already, but still cannot. Okay? Right? And therefore, once it receives the photon energy, it can come out. So, but like, don't use all those fluffy words. Just say that the Ke max electron, right, was the most loosely bound electron on the metal surface, right? And therefore, when it receives the photon's energy, when it absorbs the photon energy, it will have, it basically uses the least amount of energy, the minimum amount of energy to escape, and therefore it will have the maximum amount of Ke. Okay, so just take note of this, right? The most loosely bound electron, right, will spend or will use the least amount, a minimum amount of energy to escape the metal surface, and therefore it will have the most amount of Ke left. We okay on this? Can? Okay. Now, so we understand photon come in, electron come out, electron gains energy, right? If there's excess energy, the electron will have the extra energy, okay? And this electron is flying towards the collector plate. Now, there are two scenarios for photoelectric effect. Number one, you want the electron to touch the plate. Number two, you don't want the electron to touch the plate. Okay, these are the only two scenarios that you have for photoelectric effect. So let's start off with, I don't want the electron to touch the plate. So if I don't want the electron to touch the plate, what must happen? So the collector plate must have a stopping potential, and what kind of voltage is it? negative voltage, right? It's the most negative like the minimum negative voltage. That means the minimum negative voltage. That sounds a bit weird, right? Yeah,
the least negative to ensure that electrons just stay there.
Right. The negative voltage required to just stop the electron from touching the plate. Okay. So this electron, if it doesn't touch the plate, what would it do? The electron, if it doesn't touch the plate, what would it do? It will U-turn, right? It will U-turn and go back to this plate. Okay? Right. So if your collector plate is as a stopping potential, it will prevent the electron from touching the plate. It will U-turn. It will go back to the emitting plate. Okay?
Wait,
right.
Stop the KE max.
Yes. Because if you can stop the KE max electron, you can stop everyone else. Right? If you can stop the KE max electron, you can stop all the others. All the others can, right? But in terms of the electrons, in terms of energy of the electron has KE here. By the time it reaches here, what kind of energy does the electron have? What kind of energy does the electron have? EPE, not zero, right? EPE. So it converted all its KE into EPE here because this plate is negative, the electron is negative, so all the KE is converted into EPE at the turning point here, right? It will still turn, and will still go back, right, to the original plate. Okay? It's just that when you have stopping voltage, what happens to the galvanometer reading? Right, it's zero. How do you adjust the stopping potential? How do you adjust this? I want this negative. How do I adjust it? I adjust where? I adjust here. Right? I adjust my variable EMF. Yes, it's a variable EMF. It's an EMF with an arrow across, variable EMF. What's a rheostat? Variable resistor. Draw resistor, draw arrow across, that's a variable resistor. This is variable EMF. So you can adjust, you can adjust the V here. Right, you can adjust the V here, and when you adjust the V here, this V, the V of this collector plate will be adjusted. So if it's Vs, then the galvanometer should give you 0 amperes. Okay, so the first relationship for photoelectric effect you got to remember is this. All right, frequency affects what?
Oh no, energy frequency affects the stopping potential.
Yeah. Frequency affects the kinetic energy and therefore the stopping potential. So the higher the frequency of the incident light, the higher the Ke max of the photoelectrons, and therefore the larger the stopping potential is required. Right? So that's the relationship. Notice how this does not include the galvanometer. Right? This nothing to do with the galvanometer. I mean, the galvanometer is supposed to give you a 0 ampere reading. Right? So when you're testing frequency, Ke, and stopping potential, you literally try to stop the electron. So the electron is stopped and it flies back. Right? No reading on the no capturing of the electron on the plate, right? Galvanometer gives you 0. Okay? Right? You cannot have a situation, don't ask me, is there a situation where it's stopping potential but then there's a current? That makes no sense. It's like, it's nighttime, is the sun still in the sky? Right? Okay, it's not. It's on the other side of the earth. Okay? So you cannot have a stopping potential and then the current is still there. That makes no sense. That means you're not at stopping potential. Right? Stopping potential literally means no electrons touching the plate. Okay, the other scenario is this one, intensity and current. This is super important, right? At least over every year, I will always have students that have no idea what this equation is about. Please remember this, right? This I stands for what? Intensity. Intensity is what? Power over area. Power is energy over time. Energy, right? When you split it up for the photons, right? Energy is what? N over T HF over A. Where is N over T? What does N over T stand for? N over T is what? Rate of photons, right? The phrase that we use is rate of photons. HF, F is what? Frequency. So usually for frequency, what do we understand frequency to be? Like the frequency will be the type of light that you're using. It will represent the energy of the light that you're using, right? What kind of light has high frequency, high energy? UV, right? So towards violets, shorter wavelengths, UV, X-ray, gamma rays are all high frequency, right? So this HF here is the energy of each photon. N over T is the rate of photons. Okay, good. So when we are testing this relationship, if we have high intensity of a particular monochromatic light, means what? Means we have a high Rate of photons, right? So for this particular relationship, this is what happens, right? If you have high intensity, we're talking about the rate of photons is high. If the rate of photons is high, that means the photoelectrons emission is high, which means that current is high. Okay? Right. You want to summarize these 2 pages. These are the only 2 relationships you need to know. This one here, I summarize for you. This is F, KE max, VS related to each other. F, KE max, VS related to each other. This one here, I and I. Right, but the I different, huh? So one of the I stands for intensity, the other I stands for current, right? So current is this, right? Do we want the electron to touch the plate now? Right? So is this plate at stopping potential now? No. If this plate is at stopping potential, you won't get the current, right? In fact, what should the voltage of this plate be? Yeah, it should be positive, right? So if you're testing this, if you're trying to understand this relationship, right, it should be positive, and if it's positive, then you get a, your electrons are being attracted over like this. Okay. So sometimes they will ask you questions like this. Explain why that no matter how high I increase the positive voltage to, let's say I increase it from 10 volts, I increase it to 1000 volts, okay? Right, 1000 volts, right? The current recorded in the galvanometer does not increase beyond a certain point, right? Like no matter how positive it is, it still remains at this current here. Explain why. How do you explain this? Eh? Yeah, you got it. I'm asking you, like, if my collector plate is positive, I make it very positive, right? Right? How come the current doesn't increase any further? You're not wrong, but the phrasing is a bit weird. Yeah, it's limiting factor though. You can write down you can write this down in physics. But what's the limiting factor here? Is the rate of photons. Rate of photons. Rate of photons. All I had to hear was the correct phrase, rate of photons. The reason why the current reaches a saturation point, right? You have a saturation current is because no matter how positive, okay, you get what I'm trying to tell you here. I'm making this plate very positive. Means that I'm literally trying to attract the electrons over. Okay? Like there's no concept of KE max here already because I'm literally like, hey, come over here, right? So I'm gonna attract all of them. So the current goes through this galvanometer when it's attracted over, hits the plate, and then goes through this galvanometer here. However, even if I make the voltage of this 1000 volts, right, the current does not increase any further. But I thought that if I were to make this very, very positive, I can attract a lot of electrons and therefore the current should increase, right? Right or not? Okay, but it doesn't happen. So you are asked to explain why. Why doesn't it increase any further, right? And the key phrase was rate of photons, right? Because the limiting factor is the rate of photons here, right? The rate of photons here will control the rate of photoelectrons being emitted, and therefore there's only a maximum number of electrons per unit time that can reach this plate, even if your plate is very positive, right? And hence the current will reach a saturation value. You can say that, yeah, you can say that, or you can say that rate of photons, will limit the rate of electrons being emitted. Yeah. Okay. Yeah. So just take note that any increase in positive voltage will not increase the rate of photons being emitted, right? Because the rate of electrons being emitted, because the rate of photons is your limiting factor. Okay. Right. So this is the two. There's only these 2 relationships in the cell, right? Then you need to know how to draw the graphs, right? I think I'm not going to draw the graph now because I think I've done this graph many times already, right? You can go and catch the revision lesson I did with my previous class just now, right? I also did this graph many times already, so I'm gonna touch this graph. Okay. So to give you an overview, Yeah, this graph is the KE max versus F. KE max versus F. Okay, right? You can. I will send it to you guys. Right? I'll send it to you guys. Okay, right. Overview now. Right? What are the three main things that quantum theory can explain, but wave theory cannot? What are the three main things? These are the three main things. This, and this. Right? What are they again? The concept of minimum frequency, the concept of KE max Vs increasing with increasing frequency, and the last one is immediate emission. These are the three things. Okay? Notice that intensity and current is not one of those things. Right? Because technically speaking, intensity and current, if you increase intensity, does current increase? It does, right? That can be explained by wave. Right? I can say that, oh, right, intensity increase means more energy. More energy means more current. So that's why the intensity and current relationship, right, is not part of the quantum versus wave theory thing, right? Usually quantum wave theory, we will only use these three things, right? And what's your job here? What's your job? Your job is to explain why wave theory cannot explain these three things and how quantum theory explains these three things. Do you understand the context of what I'm saying? Your job is to memorize how quantum theory explains these three things. Your job is not to explain why it works. Your job is to explain how did Einstein use the quantum theory to explain these three phenomena, right? Then you might be thinking, am I not just regurgitating what he said? Yes, you are, right? That's the whole point of science, right? Regurgitating the same facts. 100 years from now, I don't think science will change, right? Science is going to be still like this, okay? So this is what we call quantum theory. Do you understand what the theory is? Like, if I tell you that, oh, this thing is a theory, what do you understand about that? Which is proven. So quantum theory tells us that it's a proven fact, right? It's been like, peer reviewed. It's been done a lot of experiments over and over again. This is the current working truth. Unless one day you go and research, you go and do research, but God forbid you don't, what a waste of life. All right. Then if you can come up with an even better theory than this, then your theory will be the new theory. Rothschild's theory. Right? Yeah. Okay. Right, quantum theory, right? But for now, it is a theory. So you know how some laymen, whenever we have a discussion, is like, oh, but this is just a theory, right? Then you have to correct them. Okay, theory means that it's been proven. It's the actual working thing. Okay, right? What you meant to say was that it's just a hypothesis. Ah. Okay. Anyway, yeah, you're fun at parties, right? Yes. Potential divider principle. Principle. Huh? Yeah. Principle of conservation of energy is proven. Basically, all the things that you're learning is not a hypothesis. It's the truth. It's a fact. Yeah. Principle. Okay. Discrete energy levels. What was the purpose of this experiment? What discrete? See me one value. Okay, I mean, don't give me the negative answer of like what discrete, but not continuous. I'm not asking you what is discrete. I'm asking you what thing is discrete. What energy levels? Electrons' energy levels, which is also understood as atomic energy levels. So if you see electron energy levels and atomic energy levels, it's the same thing, but be very careful because in the more recent chapter, you learn nuclear energy levels. Right? Nuclear energy levels is totally different. So when you excite the atom, what are you exciting? You're exciting the electrons. Okay? Nuclear energy levels is in which concept? How do you know that energy levels of the nucleus is discrete as well? By observing the alpha and and gamma decay, right? That's nuclear energy levels. That's nothing to do with this. This is not related to this at all. Okay, so this is your atomic discrete energy levels. All right, what is the basis of how this works? What's the electron doing? Yeah, okay, jumping. And how does it jump? Absorb energy in the form of what? Yeah, absorb what kind of energy? Yeah, photons are photons. So you got to understand, right? Discrete energy levels, right? This part of this chapter, right? Listen. This part of this chapter requires you, right? It requires you to take to understand that light exists as photons already. In order to understand discrete energy levels, we already must accept the fact that light exists as photons. Was it already proven?
Yes.
We just did what, right? We just proved it with photoelectric effect. That's why the chapter is ordered like this, right? Photoelectric effect tells us that light exists as photons. Therefore, I will use that concept and I'll use it in discrete energy levels, right? Photons come in, right? The electrons absorb, the electrons excite. But do the electrons jump out? No. What do? They jump up and down between the energy levels. Jump up, absorb photons. Jump down, emit photons. Right? Up, down, absorb, emit, absorb, emit, absorb, emit. You get what I'm saying? Okay, good. So, overview for this chapter, for this part of this chapter, right? We have a hot white light source. Why do I have to say hot? Because hot is white. Okay? Right? So when you have when they say I'm using a hot filament, when I'm using a hot filament, what is it emitting?
Photons of all colors.
Yeah, this one here will be white light, which is photons of all colors. Very good. Okay, but some students sometimes they're like, oh, this one emits electrons.
Wait, LED is not a hot white.
LED is a semiconductor, right? Yeah, don't care. None of your business. Okay. So this is a white light source. It produces all the photons. So when you disperse the colors, right, you get the, what's this called? Continuous spectrum. Continuous spectrum, right? This one here, what's this name of this thing here? Absorption spectrum, right? Yes, non-continuous, right? I mean, she's not wrong lah. It kind of like instead of being continuous, broken lah, right? Okay, fine. Okay, right.
Emission spectrum.
Then the bottom is emission spectrum. Okay, so emission spectrum tells us basically how the gas looks like when it's heated up. When you heat the gas, right, it will glow and it will emit this kind of light, right? And a collection of all these colors. So you mixing the colors is probably like blue, greenish a bit, right? There you go. That's for the like the mix of colors. So what do the lines represent? No. The lines don't represent the discrete energy level straight away.
The discrete photon colors.
Okay, correct. So the lines represent the photons that were absorbed, right? And what does it show? It shows that the photons the what? Okay, so you basically the photons are either produced, right, or absorbed when the electron transits between two energy levels. Since the lines are, lines, okay. I mean, okay, it's just basically they represent specific photons of specific energy, and therefore the transitions are specific, and hence the energy levels are discrete. Okay, so that's the thing, right? So there are some teachers out there, I don't know, maybe they just want to get rid of the students from off their backs, right? So some teachers say that, oh, you see this the line spectra here, then say you rotate it, then that's the energy levels. That's completely wrong, huh? That is completely wrong. Okay? All right. So just take note of that. Right. Sometimes they will give you something like this. Okay. I want you to translate the photons that can appear on the spectra from these energy levels. Time? No timing, no timing. Yeah. There's no marks to this. You want time practice can, right? But that will just take up one lesson's worth. What's the point? You go and do your practice at home or something like that. Okay, let's kind of like this is just estimation, okay? So usually I would draw the big energy ones first. One down, two down, three down. These three photons will be big energy, right? And I'm going to label it 1, 2, 3, okay? Right. So I would expect to see number 1 here, number 2 somewhere around here, and number 3 maybe somewhere around here like that. 1, 2, 3. Okay. Then what else would I see? Right. So anyway, if you were to label the energy levels, don't forget this 1, this 2, this 3, and this 4. Right. So 1, 2, and then and 3 like this, right? Okay. So this is like 4. No. The numbers will be so this is 4, 4, 5, and 6, right? 4, 5, and 6. So the gap between 3 and 4 is kind of big, right? 3 is the smallest energy of the big energy photons, right? And then 4 is the largest energy of the small energy photons. So 4 will be like somewhere around here, right? It's a large gap, but 5 and 6 will be quite close by. So 5 and 6 will be something like this. Okay, you will expect to see energy spectra to be like that. Okay. Do you also understand that they all might not be, like these might not be visible, like yeah, it might not all visible. So when we see a spectra like this, right, sometimes, right, this region here could be UV, right? It could be UV already down here, and then this region here could be IR already, which is not visible. That means you could only maximum get like maybe 1 or 2 visual spectra. So while you see the notes and you see your school's notes also, right? You see all these things like wow, the colors, right, from red all the way to violet. Anyway, you cannot see colors also, right, in the exam, right? Okay, just understand that sometimes the spectral lines extend beyond these regions here, right? So you got the visible spectra and then you got your non-visible spectra on the sides here like this, right? These are all just graphical representations. They don't actually show you the true, like spectra of all these elements. Okay, I mean it's just the idea of it. Okay, right. Um, to wrap up this thing, so we have the absorption emission spectra. Okay, so in this case here, we use white light to excite the gas. When you use white light to excite the gas, you will get absorption spectra, right? You can get your emission spectra. But there are 2 other methods of excitation, which is heating and using electricity. So you can use electricity, or you can heat the gas, but you won't be able to get the absorption spectra because for the absorption spectra, you need to have the color background. To have color background, you must use originally white light. So by the heating or by the electricity method, right, you will not get the absorption spectra. You can only get the emission spectra. Okay. Electron diffraction, what does this experiment do? This is the wave nature of particles, right? Wave nature of particles, you accelerate the particle, right? You diffract it through a carbon grating, you get your superposition, you get your dark rings and bright rings, right? You get your diffraction and interference. No, this is just electron diffraction experiment. Yeah, this is not double slit or single slit or anything like that. Yeah, we just use that as a diffraction grating. Okay, then we've got this thing. This thing is rare. This thing is the radiation pressure, right? Radiation pressure. That means now we calculate the momentum of the photons, right? So when the photons are absorbed by the surface, right, the surface will experience a force. You understand this? Okay, wait, one thing, right? There is this thing that has been happening in some schools exam papers, some schools tutorials and even the notes and all that, but not all schools have this. There's this thing called the Compton scattering effect. Okay, right? You have no idea what this is, don't worry, right? It's basically you fire a photon towards an electron, okay, towards the electron, then the photon will bounce off, it will scatter, and the electron will be like will basically deflected to another angle like this, and then you have this angle alpha and this angle beta. Have you ever seen this before? Yes, this one is you're just using momentum. Okay, so the Compton scattering effect is for you to fire a photon and the electron, then the photon will scatter off and the electron will also scatter off, and then you should understand that conservation of momentum, the vertical momentum of the photon is equal to the vertical momentum of the electron. We sort of have done this before, right? In one of our past lessons, right? We've done this before. Okay, all right, big question. What does this prove? Which means what? Huh? What? Yes, photons have wavelength. Photon is light, light has wavelength. Okay, so in fact, right, the Compton scattering effect was the second experiment to prove that light behaves as particles. Exactly. If the fact that the photons have momentum and the photons does this, it shows us that photons have momentum and therefore we can treat photons as particles. Okay, light behaves as particles. Second experiment. This is like the more in fact, this is like the more advanced experiment, right, to prove that light behaves as particles. Okay, and this one uses POCOMO, right, principle of conservation of momentum, right, to prove that light behaves as particles. This was the even upscale experiment. Okay, so I don't know whether this will come out, but there's been signs, right? A lot of the schools been using this in their tutorials, but okay lah, schools are really bad predictors of what's gonna come out lah. Huh? Yeah. Nobody can predict one lah, goodness. If you can predict, you let me know. I go and buy 4D already. All these spotting questions, all fluff one, all of them all gonna lie to you. Right. I mean, I can say until I get it right. I say that, oh, maybe planning will be nuclear. Planning will be nuclear, right? I just keep on saying planning will be nuclear, planning will be nuclear, right? 2020 hit. Wow, planning is nuclear. But then last common topic, remove nuclear. So they have to do the planning for that. Okay. And finally, we go to X-rays. X-rays. Okay. How are X-rays produced? What do you use? You use high energy electrons. You fire the electron at a piece of metal. You take the electron, you shoot it at a piece of metal. Okay? And what does the metal produce? The metal produces X-rays. Okay? Right. Do you understand that this is also called the reverse photoelectric effect? Reverse photoelectric effect. So photoelectric effect is what? You fire X-ray, you fire photons at the metal produce electrons. This is the other way. I fire electrons at the metal produce photons for me. Okay? Yeah. All right. So the electrons, after hitting the target metal, right? The target metal will emit X-rays. So the question is, how does it do it? How does it do that? What are the two methods? Right? So you got your Bremsstrahlung method, that means your deceleration method. But what is actually happening here? So what's the electron doing? What's the electron doing? The electron is high energy, right? It's high energy, is flying towards the target metal, right? What metal do we use? What's this metal? Yo. What? No. Huh? Tungsten? Yeah, tungsten or chromium. Right? Tungsten or chromium. No, this is tungsten. It could be tungsten. I don't care. It's just a filament. The tungsten metal is the one that's most important. Down here, the target metal. Tungsten or chromium. But why is it got to be tungsten or chromium?
Also, it don't melt.
Yeah, you have to say it, right? Why? So why does it melt? What makes it don't melt? Yeah, say it. Say the thing. Say the thing that will help people understand. Don't give the final answer so that it won't melt. Huh? Right? High melting point. Tungsten high melting point. Okay? Right? Chromium have high melting points too. Okay? Right. So the Bremsstrahlung method, how does it work? What's the electron doing as it flying towards the target metal? This is your tungsten, W. Do you know that your chemical symbol for tungsten is W? Now you know, W. Right. So the electron is flying towards this nucleus. What's happening? It decelerates. Why does it decelerate? What makes it decelerate? How does it interact with the nucleus? Attraction. The nucleus attracts the electrons. Right? So there's electrostatic force or attraction here. Okay? So the electron is attracted by the nucleus. Okay? And therefore, this is Fe, and therefore it decelerates. It turns, it makes a turn. As it makes a turn, it decelerates. So this part here is your deceleration. This is your Bremsstrahlung. Bremsstrahlung is deceleration. Okay? And the moment the electron decelerates, a photon is produced. This photon comes from where? Where does this photon come from? This is your X-ray photon. This is your X-ray photon. Where does it come from? It's a packet of energy, right? So where does the energy come from? No, it comes from the electron that's decelerating. It's just losing energy, right? Just lose energy. Lose energy. Okay? Okay, I tell you what, you just imagine that the electron, okay? You run very fast. Okay? Then someone use a rope, right? And then lasso you and then just yank you, okay, like this. Then your wallet drop out. That's your wallet dropping out. Right? So Roshni now has less money. Right? Her money came out like this. Okay? Right? But because when I talk about it in terms of money, then you suddenly remember how this works. So where does the energy come from? The energy comes from the electron, doesn't come from the target metal. Right? It doesn't come from the nucleus or anything like that. You said nucleus just now. What? It's a loss in Ke. Bremsstrahlung. Yeah, do you lose money? Where did the money become? Becomes X-ray photon. Okay? Right? When I swing you around like this, right? So then your wallet flings out. Then that's your X-ray photon. Right? Does it work in your head now? Okay, good. It actually goes on to another atom. Then it Bremsstrahlung with another dude. Right? If he has enough money, right, you just swing onto another guy. Oh, that sounds wrong, Roshni. Oh no. That sounds wrong. That's not good. Okay, but what's the one thing? What's the special thing about the X-ray photon? Like what's the special or rather what's the characteristic? Not correct. I don't want to use the word characteristic. But why is it continuous spectrum? Because the electrons they are approaching could be near or could be far, right? So the amount of energy lost by all these electrons, this random total amount of electrons lost are all different. So some electrons lose more energy, some electrons lose less. Right? So we get a spectrum of energy. We get like a range of energies that's being converted into photons. You understand this? Energy come from where again? The photon come from where? It comes from the electron, the decelerating electron. And why is it arranged? Because some electrons are near they go past near the nucleus, sometimes they go past far away from the nucleus, so they lose random amounts of energy, varying amounts of energy. It's being flung out, yeah, correct. That's right. The guy will swing you out of your money, man. Yeah, that's right. Yeah, stop throwing money at guys. Okay. Right, so down here, so you could lose a lot of energy, you could lose very little energy, so there's a varying amount of energy. Okay, and therefore you will get your continuous spectrum like this, right? This is your whoop, right? Your X-ray continuous spectrum, correct? Okay, so there's a concept of minimum lambda, right? Because these are all the wavelengths. Sometimes they try to be funny. They give you a graph of frequency. How would the frequency graph look like if they give you intensity frequency graph? How would it look like? It will look like this. Right? It's just the other way around, you know? Yeah. Right? Because there will be a maximum frequency. Right? So minimum wavelength means what? What's this X-ray photon here? This is your max energy X-ray photon. As close, this is the one that's the closest and lost the most amount of energy. Yeah, this is the one shot I lose all my money. Don't care what happens to it. You don't care. You only care about what happens to the money. Always care about the money. Don't care about what happens to him. Right? Just care about what happens to the energy. The electron can go and be lost to some other thing. I don't know. It disappears, dies off. Don't care. You just care about the money. Okay, yeah? Alright. Now the question is this. Right? So I need to backtrack to the setup again. Right? There are two voltages at play here. One is called the filament voltage, the filament PD. Filament PD. The other one is called what's this one called? Accelerating PD. Accelerating PD. Okay? Now, if you change any of these two, something will change to the graph. Okay? If you change filament PD, what happens? You get more electrons. So you increase filament PD, you will get more electrons, like this. Okay? Right? You get more filament PD means you produce more electrons, but they don't have more energy. You still need to attract them over, right? You attract them over using the accelerating PD, right? You accelerate them over to here. You increase accelerating PD, they will get more KE. So filament PD increases number of electrons, accelerating PD increases KE of electrons. Yeah, that's what I'm going to do. So if you have your continuous spectrum looking like this, like you always have to compare to a base graph. This is a base graph, right? What happens if you increase filament PD only? What happens to the graph when you have this was the original one, right? Okay, then you increase the filament PD. Filament PD increase. What will happen? You will start from the same spot on the graph and everything will be higher, right? The peak will also should be around the same as well, right? Down here like this, like that. Okay, this is increasing filament PD. So what happens if you increase accelerating PD? What? Yeah. Yeah, correct. Okay, so if you increase accelerating PD, right, your graph will look like this, right? Everything will shift towards the left. Now this graph obviously, no, yeah, everything is higher. Everything is higher. Intensity also higher because more acceleration means more energy. More energy means you can bremse along more. You can throw your money away more. More money to throw away. So the intensity is higher. Okay. Yeah, throw more money away. Like that. Okay, there you go. All right, but there's something wrong with the. Okay. Mm, mm, mm. All right. So this is your dislodging technique. What was it? Dislodge mechanism. Mechanism. Okay. The electron comes in, smacks into the inner electron of the tungsten atom. Right. The inner electron is gone. This guy is also gone. Where they go, don't care. Right. It's just that the inner shell is now empty. And if the inner what? Correct. It could be. It could be. Actually, you know what? It could be. There's no excitation. There's only de-excitation. It could be the outer electrons, right? But here's the thing: energy levels, right? Energy levels. How are energy levels arranged of the tungsten atom? So you see, right? If you dislodge the electron from the inner shell, let's say you dislodge it from the ground state, okay? Any electron that's de-exciting from the higher to down to this ground state will be a very big energy gap. These big energy gaps will appear as spikes, right, around here. Right? This is like the 2-to-1 and 3-to-1. 3-to-1 and 2-to-1. Okay? All right. But if let's say you knock out, let's say you ask me, but then is it possible that the electron will knock out one of the outer electrons? Can also. Can. Right? Let's say you knock out number 7. Knock out number 7. Who will de-excite to number 7? 8 to 7, 9 to 7. Correct? But 8 to 7, 9 to 7, what's the energy gap? The energy gap is super small. So if we are looking at those characteristic wavelengths for 8 to 7, 9 to 7, right, where are they? They're all the way here. They're all, you draw the graph, right, all the way to the end there. Like you can't see it, right? They won't appear in the graph. So these spikes here are literally the ones that's closest towards the n equals to 1. So this is like your n equals to 3 to 1, and 3 to 1, and this one is the n equals to 2 to 1. Could there be spikes here? Could there be spikes here? Actually, yes, there could be. There could be. But if there's a spike here, what is this? This is 4 to 1, right? Then could there be a 5 to 1? Why am I drawing the spikes even more and more small? Because the probability of a electron de-exciting from 4 to 1 is incredibly rare compared to 3 to 1 or 2 to 1. Right? So generally speaking, we do not draw these ones here. It's there. If you look at the true X-ray graph, right, you actually can see some of the spikes there, but it's so insignificant, nobody cares about them. Right? We only care about the one that are more probable to happen, right? Which are usually the more the more immediate ones. Speaking of probability, they may ask you, why is the second spike higher than the other spike? Like, why is this spike here, right, higher than this spike here? So no. This is a one de-excitation. So it's not 3 to 2 to 1. If you go from 3 to 2 to 1, you're going to 2 to 1 again. I'm talking about from 3 directly to 1 versus 2 to 1. Because it is more. No, it is more possible. It's more probable they go from 2 to 1 rather than from 3 to 1. So n equals to 1, n equals to 2, n equals to 3, right? The probability of 2 to 1 is higher than the probability of 3 to 1. That's why your intensity of 2 to 1 is higher. Usually speaking, if they ask you a question like this, you have to state that it's about based on the probability of it.
Wait, it's because the energy gap of 2 to 1 is more than 3 to 1.
Yeah, you can say that it's more energetically favorable. How about 3 to 2? Roshni, how about 3 to 2? No. How about 3 to 2? 3 to 2. Is it possible? It's very possible. But where is it? Yeah, not here. 3 to 2 is a very small energy gap. It's all the way at the end there, somewhere there, far away. Right? Ain't gonna happen. Okay, right. Now, if you use the same tungsten metal, the spikes would be characteristic there because the spikes represent what? The spikes represent the photons that were emitted based on the energy levels, and energy levels unique to every for every element. So if you don't change, so again one more time, right? So your graph looks like this, like that, right? So you increase filament PD. Filament PD increases, right? What would the graph look like? Right, higher intensity. Yeesh, sorry. Okay, I don't have to not cross, like, I'll just cross it like that, okay? Tell me this. You increase filament PD, right? The intensity will all increase, but everything else, like, starting minimum wavelength, right? Characteristics, all the same positions, okay? But if you increase accelerating PD, right? So if your graph is like that, you increase accelerating PD, right? Then everything will increase, right? The minimum wavelength will become shorter though, actually. So not that it increases. So tell me that. Okay, there you go. Right. So that's the way these two things works. Does that help you now? Yeah, it does, right? So I think it's important to realize that, yeah, I mean, you can have these kind of de-excitations, yes, right, but it will be far away. Oh, you're saying that when it goes from 3 to 2 to 1, so you get more chances of it happening. Okay, that's what you're saying. Okay, that's fine. I get it now. Yeah, thank you. Right, that's right. But the 3 to 2 won't appear here. The 3 to 2 will appear like far away. Okay. There was one question from a school before. What they did was this, right? They had something like that. Okay. They had 2 other spikes, and then they say that when they reduce the accelerating PD, right, only these 2 spikes could be seen, something like that, right? Then they ask you why the other spikes cannot be seen. Yeah, and basically the idea here is that the intensity is so low that it doesn't appear on the graph. Yeah, the intensity of these occurrences is so low that it doesn't appear on the graph. Okay. I am in a rush because I need to address some of my year 3, year 4s. They have an exam tomorrow, so I'm gonna stop here today. Right, we'll continue this on Thursday. Please go and do the paper 3. Yeah, let's go and do paper 3. I haven't even finished the paper 3 yet. Right, go and do the paper 3. Asked me for any. What was the video? The graph, right? Can you drop me the question, the request for the photoelectric graphs, because I skipped that part just now for revision. Continue to do the thing, and then ask me to assign a practical paper as well. And then what else? Yeah. 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 Hey, do leh. Just do, cause if I want to do more than the TYS, I got to, Yeah. Is your school going through TYS in, like, at all? Not at all. Wow, the east side all don't care one. Yeah, the east side all don't care one, no. Walao. So the thing is that I might be going through 2020, 2021 TYS, because if I checked on Thursday's class, apparently those are the 2 TYSs they're going to do. Okay lah, no choice. I have to see majority lah. Really? Okay, I think then it's a bit too fast. All right. Bye bye. Right, those online, thanks very much. See you on Thursday. Bye bye.